This section is going to just have some examples that you might like to see regarding Burnside's theorem and other things, so that you have some problems to work with and base around with. Okay, so last time we saw how to figure out the number of ways of coloring different colorings of a rectangle with two colors, red and blue, right? We counted the different compositions it could be, and we said that, oh, total it was 48 divided by the order of the group, which was 8, order of the, what do you call it? A dihedral group of order 8, and we got a group of symmetries of a square, which is order 8, and we divided by that 48 by that and got 6, right? So now example, x is equal to, again, we are going to take group, what do you call it? Vertices of a rectangle, vertices of a square, not a rectangle, square, which will denote 1, 2, 3, 4, and my group G is is 1 r squared r cubed tau. T was the reflection. T, r composed T, r squared composed T, and r cubed composed T, right? Let us assume that we have the same thing. Now assume we have P different colors. Given P distinct colors, okay, let C is equal to set of colorings of X with the P colors. So order of C is equal to order of C is equal to P to the 4, right? Every vertex has 4 choices, so total number of colorings is P to the 4. Find NGC, which is find the number of what was the exact word? I forgot. Non-equivalent colorings. Okay, we want to find the non-equivalent colorings, and the solution is going to be exactly the same as previous case. Okay, in previous case part we did P is equal to 2. For general case, replace 2 by P. So in the last part, you would have seen that we were writing 2 squared, 2 cube, and other things, and that was just so that we can explicitly translate it into in the P case effectively. So for the identity permutation, we had P to the 4. Previous case, we had 2 to the 2. Right, 2 to the 4. Identity permutation keeps every coloring the same, right? The rotation has only P choices, right? Where everything is same. When I have R squared, I get P squared choices, because now the opposite corners have to be of the same color. R cube, again P choices, as before. Tau, or T, not tau. I was saying T. I mean, general notation uses tau and rho, but I'm using T and P. T and R. Reflection has p squared choices. Again, last time we did A, B, B, A, B, A, B, right? And that gave me p squared choices. R composed T gave me p cubed choices. R composed T squared gave p squared choices, and R composed T cube by symmetry gives p cubed choices. And so the total is p to the 4 plus 2p cubed plus 3p squared plus 2p. And therefore, NGC is equal to p to the 4 plus 2p cubed plus 3p squared plus 2p divided by the order of the symmetry group, which in our case is 8. Okay. Let us do some other examples. Example, consider the multiset. Consider the multiset S is equal to infinity times A, infinity times B, infinity times C, and infinity times D. Okay, fix integer, fix n greater than or equal to 1. Okay, so we are not saying that these are now on a square. These are just for random numbers, right? Recall, well, total number of permutations, number of terms of S is equal to 4 to the n, right? Every element has n choices. How many permutations? How many n perms of S are not equivalent under the equivalence if we declare well, how many permutations of S, how many n perms of S, how many classes of how many equivalence classes? Let me rephrase this question. How many equivalence classes of n perms of S are there under the equivalence A1, A2, an is equivalent to an minus 1, A2, A1. So I am saying that only mirror images are equivalent, and we are trying to look for this. Okay. Solution. Well, define x is equal to 1 to n, right? There are n elements in my group. I'm going to call them 1 to n. View VIEW, not V. I view A, B, C, D as colors, A, B, C, and D as colors, because that's what I'm looking at. Therefore, C is equal to set of all colorings of X with A, B, C, and D, and order of C is equal to 4 to the n. Now, what is my G? Well, what is the only equivalence I have? It is the mirror equivalence, right? I am reflecting it around the midline, and that is my only equivalence. And so I can say my group is define G is equal to I comma T, or tau. Well, I'm going to use tau because I keep drawing tau. So tau in this case is 1 2 dot 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 n, and n minus 1 dot 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 1. Great. Tau squared we know is identity, and therefore G is a permutation group. Therefore G is a permutation group, and I can use Burnside's lemma. Well, want to find the number of non-equivalent equivalence classes of this, which is exactly NGC, right? By Burnside's theorem, I just have to divide it into two cases. I have to find CF for both of these. F belongs to G, CF, and cardinality of CF. Well, suppose the permutation is identity. Well, what does it keep? It keeps the entire C the same, right? Entire C is preserved always under identity, and so this cardinality is 4 to the n. Now, what is preserved under reflection? For tau, let us consider two cases. Case 1, R is even, n is equal to 2r, is even, and so then the reflection happens around a1 a2 dot 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 ar, reflect ar dot 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 a2 a1, and therefore number of choices is equal to a1 to ar, which are in a b c d, and so we get 4 to the r, which is 4 to the n over 2. I'm not writing it as 4 to the n over 2 because I want to be slightly lazy. Case 2, n is equal to 2r plus 1 is odd, right? Now, if n is odd, how does my permutation look? Well, a1, a2, dot, 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 ar, and then I have an ar plus 1, but my line of reflection hits around ar plus 1. Then I again have ar to a2, a1. And so the total number of choices now is a1, a2, up to ar, but also ar plus 1. That is also something I can choose. It can be any of the four colors, A, B, C, D. And so the total number of choices is 4 to the r plus 1. Right? So it depends on whether n is even or odd. And I have a nice way of writing this function. So ng of c is equal to 4 to the 4 to the n plus, well, in the even case it's 4 to the n over 2. In the odd case it's not 4 to the n over 2. It's more than 4 to the n over 2, right? It's 4 to the n plus 1 over 2. What function do I know that does that? It's the ceiling function. So I have ceiling function of 4 to the n over 2 all over 2. Stop. Okay, and that's the number of symmetries I have. Okay, let us try to do now for a tetrahedron. Example. Tetrahedron. Now my drawing isn't spectacular, as you all know by now, but this is what my figure of tetrahedron is going to look like. It's in 3 dimensions. Okay, and this is either the top view or the side view or whatever view you want. So I'm going to label these vertices as 1, 2, 3, and 4. Okay, so let x be x is equal to set of vertices, which in this case is 1, 2, 3, and 4. Okay, and let G be the group of symmetries of tetrahedron. G is equal to group of symmetries. Group of symmetries of tetrahedron. And we have our first big problem. How many symmetries does a tetrahedron have? What can we find? Well, let's try to do it as we always do. Try to find out the rotations and then try to find out the reflections. So, oops. Let us try to find types of symmetries. In G, and number of them. Okay, so if you look at it, it is more or less an equilateral triangle, right? That means if I keep one of the vertices constant and I just rotate around it, that is going to give me 120-degree clockwise. By keeping maybe vertex 4 constant, and I rotate them this way. Well, I have 4 choices for the vertex that I am keeping constant, so there are 4 of these clockwise. Well, I can do the other way around, counterclockwise. Exactly the same idea. Now I'm rotating it this way. Again, it depends only on which vertex I'm keeping constant. So I get 4. And now there is another fancy, oops. Stop, go up. And there's one more fancy rotation that is allowed, and that is a 180-degree rotation around not one of the major axes, but if you draw it like this, then it's going to be between the two opposite sides. You take these two opposite sides and you draw a line through them, okay? And that is going to give you something that you can rotate around for 180 degrees. Because once you do it, it's going to flip the two vertices joining that edge. Okay? And how many edges do I have that I can choose? Well, I have 3 edges that I can choose, right? The 3 bottom edges. And whenever I choose one bottom edge, the opposite edge is fixed. And so I have 3 edges like this. And I'm forgetting one thing, which is the identity. There's exactly one identity, and that's 1. And so the total number of rotations is 12. Okay? And this is often called the alternating group of order 12. Alternating group of order 4 for a tetrahedron will only allow the physically possible symmetries, and that means order G is equal to 12. Okay, and this is called the alternating group of order G is equal to alternating group of order 12, which is actually denoted A4. Okay, So alternating group of order 4 has 12 elements. Well, now we need to figure out how many symmetries it has, right? And so either we can describe in terms of colorings and define each equivalence class, or I can be smart. I will use Burnside's lemma. Okay, sorry, Burnside's theorem. So consider each rotation and see what it keeps common. Ugh, I hate when this happens. Why are you not listening to me properly today? Well, F belongs to G, C of F, and order C of F. Well, initially we'll do this for 2 colors, okay? And then you'll notice that, well, the same exact idea as previously can be generalized to more than 2 colors. Okay? So 120-degree clockwise. Well, when I'm doing 120 degrees clockwise, I have only 2 choices. The fixed vertex A, and all others have to be of the same exact color, right? And so I get AB belong to RB, and that is 2 to the 4 is equal to, 2 squared, because I have 2 choices, which is 4. 120 degrees, I missed, counterclockwise. Same exact reason. I have 1 vertex that's being kept constant. All the other 3 have to have the same color. If under rotation, they're being kept the same. So AP in RB. What is wrong with you today? And that's 2 squared is equal to 4 for this also. Now comes the slightly trickier rotation, 180 degrees rotation. Let us see. Now, if my tetrahedron was like this, and I have a line passing through these 2 edges, what is going to happen? When I rotate, these 2 vertices are going to go to each other, and these 2 vertices are going to go to each other, right? And so again, I have exactly 2 choices, and so I get 2 squared is equal to 4. And for the last rotation, I is going to be all of C, which is 2 to the 4 is equal to 16. Therefore, NGC is equal to summation F belongs to G, C of F over absolute value of G, which is equal to, well, sum of all of that is 12 plus 16, which is 28. No, sorry. Each of these is multiplied by the correct number of rotations. So 4 into 4 plus 4 into 4, because there are 4 clockwise, 4 anti-clockwise. There are 3 into 4 180-degree rotations, and 1 into 16 all over order of G, which is 12, which is equal to 4 for 16, 32, 12, 44 plus 16, 50, 60 over 12, which is 5. Okay, and so we have 5 of these rotations. If I was to try and do this by with n colors or p colors, oops, if p colors, replace 2 by p, and we get what? Right. What's the formula? Right. We would get n ngc is equal to, well, 4 rotations. Each gives me p squared colorings plus 4 rotations, which again gives p squared colorings, plus 3 rotations, which give p squared coloring, plus 1 rotation, which gives p to the 4 colorings, all over 12, which is equal to 4, 4, 8, 11 p squared plus p to the 4 over 12, which can be written as p squared times p squared plus 11 all over 12. Okay? So that's how we should do for different colorings. Now, if we wanted to do something else, suppose I am looking at, there are a couple more examples in the book. I will leave them to you to work out, but this should in a way provide you with some worked out examples in the case of a specific p, which is 2, as well as a random p, right? Most of the other examples are easier since we did tetrahedron, which is more complicated in a way, right? If we did necklace or something, that's again symmetry exactly the same way. And yeah, I'll stop it here. Actually, should I do this problem? Okay, let me do this problem. This is an easy example, but just so you have some practice. We have seen this before. How many ways are there? How many ways to arrange n distinct objects in a circle? Well, we know that answer. Well, this is going to be equivalent to the colorings of non-equivalent colorings of same as non-equivalent colorings of corners or vertices of a regular n-gon, with with respect to the cyclic group of rotations. How many rotations are there? Okay, well, let x is equal to 1 dot 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 1 2 dot 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 n be the vertices, and there are n colors. Well, I'm going to say c is equal to number of ways of coloring, n factorial C is equal to ways of coloring, right? And now order of C is equal to n factorial. And that's because, well, I can't use the same color twice. So I have only one of each object, right? And distinct objects in a circle. The cyclic group G is equal to identity r squared all the way to r to the n minus 1. Okay, where each rotation is by something. Let us look at how many things are fixed by a rotation. How do I do this? Right. F in G, CF, and order of CF. Well, identity permutation fixes how many? Well, it fixes the entire group CF. Sorry, it fixes the entire group C, and so this is n factorial. What about r to the n minus 1? Well, if I rotate a permutation, right, I can't have vertex 1 and vertex 2 have the same color because I can use every color exactly once. So these fix nothing. All of these fix the empty set. There is nothing that they fix. So 0. Therefore, total number is equal to stop n factorial. And therefore NGC is equal to 1 into n factorial plus 0 plus 0 plus dot 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 plus 0 all the way over n. This should have been a factorial, which is equal to n minus 1 factorial. Okay. So that is how you do for something like a necklace or points on an octagon or something. Okay. So, yeah, that's some of the solved problems. Hope this gave you some idea how to use the theorem for more than two colors or in general. Okay.